Okay, are you guys all on whatever page I told you?
11.
Page 11 or something? Okay, so today we're doing section 1. We're doing section 1 today, tomorrow, and Thursday. So we're going to talk about a hypothesis testing procedure for the difference in population means. So before today, we did hypothesis tests with one population. We either looked at proportion or we looked at mean. Today, we're going to be comparing two different populations. So we're going to talk about hypothesis tests and confidence intervals. Okay, so first thing that I want to review with you is how to design an experiment. There are 4 things that you have to talk about when you're designing an experiment. You guys remember what they are?
Wait, what? What's the question?
If I asked you to design an experiment,
Okay. I need some variables of independence.
okay, let me give you an actual example. So we are going to compare 2 different treatments. So for example, we did a lot of examples that had to do with like lowering your blood pressure. And a lot of times they compared a new drug to the current drug. So the problem I'm going to give you is you have 100 subjects. You are comparing the old drug or the current drug to the new drug, and you want to see which one lowers the blood pressure better. Design an experiment. What would you have to talk about?
Random assignment?
So you're going to talk about how you're going to randomize people. What does he mean by that?
Who gets what treatment?
How you're going to put them in groups. Okay, what next? So I have 2 groups of size 50 each. Then what?
Which group gets the treatment?
Okay, so then you're going to talk about what treatments they get. What next?
How you carry out the experiment itself.
Yeah, how you carry out the experiment and what you measure. So we're going to measure the blood pressure before and after. And then what last?
Comparing the results.
Compare. Yeah, so previously you guys said something like, we're going to compare the average reduction in blood pressure. Now that's not specific enough. You're still going to have to say that you compare, but you're going to have to tell me exactly what procedure is being used. So you're going to have to tell me, I'm going to use a 2-sample t-test for the difference in means. Or I'm going to use a 2-sample z-test for the difference in means. Or I'm going to use a 2-sample z-test for the difference in proportions. Now when you design an experiment, you have to be very specific. Proportions is the last thing that we're going to talk about this chapter. Today we're going to talk about difference in means, t versus z. So that should all be review. Okay, so we're talking about a 2-sample t-test. There are 2 times when this is going to come up. The first one is, I want to know, are 2 population means equal? So, for example, maybe all you have on your note sheet is an example. So it has the back page that's blank that you can write on. Okay. So the first case where you're going to use today's test is when you're comparing 2 different populations. So maybe I want to know who can jump higher, males or females. So I want to know, is the population mean female jump height the same as the population mean male jump height? So I'm comparing 2 separate populations. So that's the first case. Second case is you're comparing a subpopulation to the greater population. So this case, I might want to know, do the seniors have the same average working time as all of prospect students? So you guys as seniors, you are contained within prospect students. So I'm comparing you to the rest of the prospect students. So you're going to test, are those equal? Like before, this can be 2-tailed, upper-tailed, or lower-tailed. Okay, so I think it's best if we just do an example. So this is the one that you guys have on page 11. It says, the example we will use comes from a 1975 experiment that attempted to modify the weather. The following information is from the original study. So clouds were randomly seeded or not with silver nitrate. Rainfall amounts were recorded from the clouds. The purpose of the experiment was to determine if cloud seeding increases rainfall. Okay, So here's the data. Rainfall from cloud seeding. The rainfall in acre feet from 52 clouds, 26 of which were chosen at random and seeded with silver nitrate. They took 52 clouds, they split them into 2 groups. Half of them got silver nitrate, which is called seeding, and half of them didn't. And then they recorded the rainfall from the 2 groups. What they wanted to know is, do those clouds that have the silver nitrate, do they produce more rainfall? With me? Okay. Okay, so this is the data that you guys currently have. Right now, I want you to put unseeded in list 1 and seeded in list 2.
Unseeded in list 1?
I would prefer unseeded in list 1, yes. Okay, do we have 2 lists that have 26 in them?
Mm-hmm.
Yeah, everybody does? Okay. Okay, so I think the first thing that we're going to do is we're going to carry out the hypothesis test, and then from there we're going to look at the rest of the stuff that's on your sheet. So if I were you, I would write this on page 12. I'm not going to do the entire hypothesis test. I'm going to do what's different, okay? So first thing that you're going to have to do is you're going to have to define your parameters. In this case, you have 2 parameters. So we're going to have mu1 and mu2. So mu1 is going to be the population mean rainfall. For, let's say, the unseeded clouds. Mu2 is going to be the same thing except for the seeded clouds. In H, you're still going to define your null and your alternative. it's written as a difference in means. So your null is going to be that mu1 minus mu2 equals 0. Okay, so this tells us there is generally no difference in rainfall amounts between seeded and unseeded clouds. Okay, you have to say generally because we're looking at population means. So it's not going to be true for every single pair of seeded and unseeded clouds. So it's going to be a general trend. So then your alternative is mu1 minus mu2. Okay, so they wanted to know, is the rainfall greater for the seeded clouds? So thinking about that, they want to know, is mu2 greater than mu1? So do the seeded clouds have greater rainfall than the unseeded? That means mu1 minus mu2 is going to be less than 0. I don't want you to write this. Personally, I write that to get it straight in my head and then I erase it. So this would tell us that generally the seeded clouds have greater rainfall. With me so far? Can I keep going?
Yep.
Okay. So, A, your assumptions. These are going to be pretty similar, but they're going to change a tiny bit. What is your first assumption normally? Random sample. Okay, so it's going to be similar, not the same. This time you have to have independent random samples. So independent means that choice of one sample is unrelated to choice of the other sample. Is that true here?
Yeah.
Is my choice of unseeded clouds independent from the choice of seeded clouds?
Yes.
Yeah, fairly. That one pretty much is always going to be true. But in the next section, we're going to talk about samples that are not independent. So what we're doing today is just for independent samples. What is the second assumption normally? Okay, so in this case, we're going to do approximately normal, sampling, distributions. So in other words, you have to check for both samples, for seeded and unseeded. The three cases still exist from before. So either they tell you both populations are normal, or you can use the central limit theorem on both. So that would be n is greater than 30. Or you look at a box plot of the sample. In this case, what do you think you're going to do? Or I guess box plot of samples. Are you told that the population is normal from what I've told you so far? Nope. Does the central limit theorem apply?
Nope.
Nope. So you would draw two separate box plots. Can I assume that you are okay drawing your own box plot? Okay, so we're going to skip that. These are the only two assumptions that you have to check. Going on to n. You still have to tell me tails. So in this case, we did less than 0, right? So it's going to be lower tailed. You have to tell me the test name. So this is a hypothesis test for the difference in population means. Of course, don't abbreviate it like that, actually write it out. Alpha is going to be 0.05. Last thing you have to tell me is the table. In the case of mean, do you guys remember from last chapter that with mean sometimes it's t and sometimes it's z? Same thing applies here. Do you think it's t or z? T. So you're going to use the t critical values table. What do you have to remember anytime you use this table? Degrees of freedom. Okay, so in this case, here's how you calculate degrees of freedom. You're going to do n1 minus 1, you're going to do n2 minus 1, and you're going to choose the small. So n1 and n2 just mean from your two samples. So my first sample is size 26, so I'm going to do 26 minus 1 and get 25. Second sample, same thing, it's size 26, I subtract 1 and I'm going to get 25. So in this case, it doesn't really matter, they're the same, so you're going to use 25 degrees of freedom. Oftentimes, you're going to have samples that are different sizes.
You said you use the smaller one?
Mm-hmm.
Why is that?
It's just a conservative estimate. There's actually this really long degrees of freedom formula. This is the real degrees of freedom formula.
What's the t? What is it?
This is the real degrees of freedom formula. So really, you're supposed to calculate your degrees of freedom this way and use that. This is going to end up a little bit bigger than this. So ours is always a conservative estimate. You are not going to do that, ever. Please don't waste your time doing that.
I don't even know what those things mean.
I am going to show you how to do this on the calculator. You just need to know on the calculator, it's always going to use this degrees of freedom. So your answer is always going to be a little bit off the calculator. Our way is not wrong, it's just a little easier. Okay, can I keep going? Okay. So next part is our t. Okay, so again, we said we're using t and not z. Our sample statistic in this case is x1 bar minus x2 bar minus the null. The null is mu1 minus mu2 all over square root of s1 squared over n1 plus s2 squared over n2. Okay, so x1 bar and x2 bar you're going to have to find on the calculator. So you're going to have to do 1 bar stats twice. So do your 1 bar stats for L1. I got an x bar of 164.59. Okay, and then let's be smart and write down the standard deviation. 278.43 squared over 26. Now do the same thing, do 1 var stats, except do it for list 2 this time. And you get an x bar of 441.98. And you get a standard deviation of 650.79. Okay, and then in the numerator, we still have to subtract our null, which is 0. In general, you're pretty much always going to assume that there's no difference. Okay, right now you guys calculate this, please. I have no idea if mine is right. So I would love verification that mine is right or wrong. Yeah, you got the same thing? Okay, did we all do okay with that? In this case, I don't care that you store the values. Because there's just too many, so you don't have to go back and find XX and all that. This time you can use rounded values. Okay, so from here, we have to find the probability that t is less than or equal to -2. Remember that your degrees of freedom are 25. You guys like using the table or the calculator? Calculator. So on the calculator, you're going to do t CDF. My lower bound is -1 times 10 to the 99th. I'm going up to -2, and I have 25 degrees of freedom. I got 0.0283. Yeah. Okay, so we'll do the O at some point, but let's just jump right down to M. You would do 0.0283 is less than my 0.05, so I'm going to reject the null. Okay. So, drawing your graph. You're still going to have the 0, 1, 2, 3, and then the -1, -2, -3. Okay, our null is 0, so in this case, you're going to have another 0. Standard deviation is everything in the denominator. So do that, everything in the denominator right now, and see if you get the same standard deviation that I'm going to. I got about 139. Yeah. 139, 278, -139, -278. Okay, one thing I found on your test is that a lot of you are just kind of shading in random spots on your graph. How do you know where to shade? Some of you are just like picking a point and shading there. Like, bam, I'm going to shade from here this way. The t value. So t is -2, so I go to -2. It's lower tailed, so I'm going to go this way. What I want you to label above this is the t value and the sample statistic. In this case, this is our sample statistic. Which is -277.39. Okay, so now I see that this makes sense. -2 and -2 match up. -277 and -278 match up. And lastly, you've got to look at, does that look like the same area as my probability? I got a probability of 0.0283. That looks like about 0.02. With me so far? Yeah? Okay, last thing I want to do is write a conclusion just to get us some more practice with that.
Is it roughly the same?
Uh-huh. Yep. So we're going to say, based on my analysis, I reject the null. And instead believe that the population mean rainfall for the seeded clouds is greater than for unseated. Before I go on, what does that mean to us? Why do we care? Like, what does it mean to the people who are actually carrying out this experiment? What do you think they concluded from their experiment?
Seeding clouds does work.
Yeah, the seeding clouds does work. That's the whole point of why they did this, is, yeah, seeding clouds does work. Do you guys know they actually do this?
No.
They seed clouds in areas that, like, are going through a drought, mostly farm communities. Can't remember where else. But they actually do seed clouds. Okay. And then the probability of obtaining a difference in sample means. So that's just saying we took our sample means and we subtracted them, of negative 277.39, assuming no difference, is too rare or not rare enough? Too rare. I reject, that means too rare. It's too rare to attribute the difference to random chance fluctuations about 0. Okay, a lot of you, when you write this conclusion, write things that don't really make sense. So I want to make sure that we understand this. So that negative 277 is what happened. We assumed that there was no difference. Is too rare to attribute the difference. What difference is this talking about? No, I don't think so. So we say difference, difference, difference. This difference is not the same as these two. What is that difference referring to?
The difference between the populations.
So this is that what you mean?
Yeah, I guess.
Okay. So difference in sample means that's x1 bar minus x2 bar. Assuming no difference, where did we assume no difference? The null, right? So that was the mu1 minus mu2 equals 0. This difference is talking about the difference between what we expect, the mu1 minus mu2, as compared to what actually happened. So this difference is talking about the difference between what we expect and what actually happened. Remember how we talked about because of variability, what we expect is not always going to happen? So this is saying, I got a difference between what I expected and what happened, and that difference was way too big. It was way too rare. So I'm thinking the difference between these two didn't happen because of chance. Why do we think it happened?
There's an actual difference in
They
seeding.
seeded the clouds.
Because our null is wrong. Our null assumed that there would be no difference in the seeding and unseeding. Because we got a result that's not consistent with that, we're saying we think that our initial assumption was wrong. That's what this difference refers to. Does that make sense? Okay, how do we feel about this new procedure? It really should be too different. Little tiny bit more work, but not really all that different. Do we have any questions? No? Okay. I want to look at some of the other stuff that you guys have. This, you don't have, but just look at it. This is Minitab output. Minitab is a computer program. Well, it's actually Fathom. It's a computer program where you put in all your data and it computes some stuff for you. So this is seated and unseated, and it gives you 3 numbers. It's telling you that the 3 numbers are mean, standard deviation, and what is count?
No,
And sample size. So those are the numbers that we got. This is what you have on the bottom of page 11. This is actually Minitab. Okay, so N is your 2 sample sizes. So here are my sample sizes for the unseated and the seated. Here are the 2 sample means. SE of mean, do you know what that is? The standard error. Yeah, you guys remember what that means? We just did that like 2 chapters ago. Standard error. No? You remember the formula?
Square root of SS was it or something?
That's a different standard error. This one is S over root N. So they took the standard deviation and they divided by the square root of N. Minimum Q1, median Q3, maximum. Why did they give you this? The 5-number summary, which is used for box plot. Yeah. Okay, here's the dot plot. So if you drew a box plot, or in this case a dot plot, why would I bother to give this to you? Do you remember how we talked about when we were doing the phantoms that you would have to draw a box plot and then we just skipped over it? So this is a dot plot instead. Does this show extreme skewness or outliers? Yeah, so do we think the 2 sampling distributions are approximately normal? What would we have to say then? We are going to assume the populations are normal. So in this case, you would say, my sample sizes are not bigger than 30. I can't use the central limit theorem. My samples show skewness. I'm going to assume the populations are normal and proceed with caution. Okay. This is on the next page. This is on page 13. This is actually really cool. This is where Minitab actually did the hypothesis test for you. So in this case, they looked at unseated minus seated, so that's exactly what we did. Estimate for the difference, that negative 277, what is that actually? If you had to put a symbol or symbols to it.
X bar 1 minus X bar 2.
Yeah, so this here, this is x1 bar minus x2 bar. And then the t-test of the difference, this is what we just did. So this 0, they mean that that's the null. So we're assuming 0. This less than, this is your alternative. This is the t-value that we got. This is the p-value that we got. They have a different degrees of freedom. So remember how I wrote that degrees of freedom formula up here and I said we're not going to use that? That's where they got this degrees of freedom. So
It's very different.
yeah, a little bit. The AP test will take either one, so there's no point doing all that work. Okay, we're going to skip that. I'll show you how to do that eventually. Oh, so here's the information about cloud seeding. I know you guys definitely can't see this, but it says the largest cloud seeding system in the world is China. So they do it particularly over increasingly arid regions, including Beijing. They fire silver iodide rockets into the sky where rain is desired. There is political strife caused by neighboring regions which accuse each other of stealing rain. It says about 24 countries currently practice weather modification. So cloud seeding was used in Beijing before the 2008 Olympic Games to clear the air of pollution.
Yeah, it was. It's nasty air.
It says in the United States, cloud seeding is used to increase precipitation in areas experiencing drought, to reduce the size of hailstones that form in thunderstorms, and to reduce the amount of fog. Oh, and it's also used by ski resorts. Fun fact. Okay, we're gonna write down one more thing, okay? Do you guys remember how Panic and Phantoms are just so incredibly similar?
Yeah.
And so the entire Panic when we just did the entire Phantoms?
Yeah.
Okay. P is the same. A is the same. N is pretty similar. Okay, so what really changes is the interval itself. So this is what I want you to write down. If you are doing a panic, here's the formula. X bar 1 minus X2 bar plus or minus T. And then the S1 squared over N1 plus S2 squared over N2. I didn't write this down in the Phantoms, but I do want you to know, or at least realize, that sometimes you're going to use Z. You guys know that, right? Depending on if you know the population standard deviations. And in this case, it's going to be sigma squared. You guys are going to have to go back and review the conclusions and exactly what goes in N. So for example, in N, you're not going to have alpha. What are you going to have instead?
The confidence.
The confidence level, like 95% confidence. Any questions? Okay, the next 2 days we are going to do examples on this. Your quiz is going to be on Friday. Your homework is due on Thursday.